Hello students, welcome to AIMS India online classes. This is chemistry session. Here we are discussing about the chapter atomic structure. In this session, we are going to see a practice sheet related to this chapter, atomic structure, based upon the concepts we have seen in the earlier sessions. So first let us say about single correct answer type questions. First among them is the idea of smallest unit of matter was proposed by who proposed it? Yes, in the a hint also given here, the smallest unit of matter, that is about Anu and Paramanus. This concept was given by ancient Indian philosopher Maharshi Kannad. He told that every padartha is made up of small particles called Anus. These Anus are composite of still smaller particles called Paramanus. These Paramanus are the smallest particles of every matter. Okay, it was given by Maharshi Kannad. Next one, quantum theory of radiation was proposed by. Yes, the quantum theory of radiation states that energy emitted by the particles like electrons is not continuous. It is discontinuous in the form of small packets. Those packets of energy are called as quanta. This theory was proposed by Max Planck, that we say as Planck's quantum theory also. Okay, quantum theory of radiation was proposed by Max Planck. Which of the following relations is correct? See, about electromagnetic radiation characteristics, some relations are mentioned here. See, one of first among them, nu is equal to c by lambda. Yes, wavelength and frequency both are inversely proportional to one another. So to remove the proportionality, it is taken here a constant called velocity of light. So nu is equal to c by lambda is a correct relation. So the next one, energy and frequency relation. We know energy of a photon is directly proportional to frequency of that radiation. Frequency of that radiation. So as it is directly proportional, to remove the proportionality here a constant h is taken, which is called Planck's constant. So the relation E is equal to h nu is also correct. Next one, wave number is equal to reciprocal of wavelength. Yes, it is also correct. Wave number is actually the reciprocal of wavelength. So these three relations are correct. Now the answer will be all of these. Next one, work function h nu naught is equal to. So according to photoelectric effect, we have relation the total energy passed onto a metal surface is equal to work function of that metal, nothing but threshold energy, or the energy required to eject the electrons by the metal is called work function or threshold energy, which is taken as h nu naught, and the remaining energy in the total energy sent will be converted into the kinetic energy of that electron ejected, that is half mv square, where mv represents the mass of that electron. Now they're asking to find the work function or threshold energy. So let us keep this h nu naught as a subject. So this will come to this side. Now, or if you keep this here itself, this half mv square will come to that side. Now h nu naught is equal to h nu minus half mv square. Total energy minus kinetic energy of that electron ejected will give the work function of that that metal surface. So where is it? Here, h nu minus half mv square. In hydrogen spectrum, which one of the following series lies in the ultraviolet region? Yes, we know in hydrogen spectrum, it was observed different series are obtained in different regions. In the visible region, Balmer series is obtained. In the ultraviolet region, Lyman series is obtained. In the infrared region, three different series are obtained. They are Brocket series, P-Fund series, and Fasken series. These are observed in the infrared region. So the series which is lying in the ultraviolet region is Lyman series. The metal best used in photoelectric cells is, yes, generally the photoelectric effect is nothing but ejection of electrons when a photon of light is passed on to the metal surface. So the metal which is having less ionization energy can show this photoelectric effect very effectively. We know the first group elements of the periodic table, which are also called alkali metals. They have greater sizes. As the size is more, their ionization energies are very less. So those metals present in the alkali metals or the first group metals can show this photoelectric effect easily. And even out of those, the one with a greater size among them is cesium. So it will be having the lowest ionization energy among those all. So it can show the photoelectric effect very effectively. With the low energy itself, it can eject the electrons and it can show the photoelectric effect. That is why mostly cesium is used in photoelectric cells. Okay, next. In Zeeman effect, the splitting of spectral lines under the influence of, yes, actually these we discuss in defects or drawbacks of Bohr's model of atom. There we say Bohr could not explain the splitting of spectral lines in the presence of magnetic field and electric field. So these were later discovered and identified by the scientists Zeeman and Stark. So in the honor of their name, they are called as Zeeman effect and Stark effect. So the splitting of spectral lines in the presence of magnetic field is called Zeeman effect. Okay, the splitting of spectral lines in the presence of magnetic field is called Zeeman effect. The splitting of the spectral lines in the presence of electric field is called Stark effect. Okay, next. The concept of elliptical orbits was introduced by, yes, based upon the same, this Zeeman effect and Stark effect, they came to know and they came to one conclusion that each energy shell is having or divided into different sub energy levels or sub energy states. Because of that, electrons are getting different quantities of energy and exhibiting different spectral lines. So this concept was explained by Sommerfeld. He told that all the electrons in an orbit are not revolving in the circular paths. Some they are revolving in the circular paths, and some of them they are revolving in the elliptical orbits also. It was explained by Sommerfeld. Next, as the velocity of particle increases, or as the velocity of the moving particle increases, the de Broglie's wavelength, what happens to de Broglie's wavelength as the velocity increases? We know according to de Broglie's wavelength equation, lambda is equal to h by mv. See here how this wavelength and velocity of the particle related, can be written as lambda is inversely proportional to velocity. So if the velocity of the moving particle increases, what happens to the wavelength? It decreases because both are inversely proportional in this. As velocity increases, wavelength decreases because the formula for the wavelength given by de Broglie is lambda is equal to h by mv. So we can say wavelength of that moving particle is inversely proportional to velocity of that particle. Okay, next, uncertainty principle was proposed by, yes, this uncertainty principle, the which states that the calculation, we cannot calculate the position and velocity of a moving particle, position and momentum of a highly the particle which is revolving with high velocity. For that, we cannot calculate the position and momentum exactly simultaneously. If we calculate both at once simultaneously, we may get some errors in those. So that was proposed by scientist Heisenberg. So it is called Heisenberg's uncertainty principle. It states that we cannot calculate the position and momentum of a particle which is revolving with a high velocity like electron. So we cannot calculate these two simultaneously accurately. So if you calculate both at once simultaneously, we may get some errors in those values. So those we call these errors as uncertainties. So this principle is called as Heisenberg's uncertainty principle. Who proposed magnetic quantum number? What are quantum numbers? The numbers which are used to locate an electron in an atom are called quantum numbers. There will be a set of 4 quantum numbers for every electron. Out of those, the first one is a principal quantum number which was proposed by scientist Niels Bohr. Second one, azimuthal quantum number or angular quantum number which was proposed by Sommerfeld. Third one, magnetic quantum number which was proposed by Lande. And the fourth one, we know spin quantum number which was proposed by two scientists Willenbeck and Goudsmit. Now here they asked about magnetic quantum number which was proposed by Lande. Which of the following has same n plus L value as that of 3p subshell? See, first let us calculate the n plus L value of this 3p subshell. What is n value for this? 3. And L value is given based upon the subshell in which the electron is located. So as it is shown here, p subshell L value will be 1. So totally n plus L value for this 3p subshell is 4. See, which of the following subshells is having the same n plus L value as 4 will be the correct answer. So now calculate the n plus L value for this 4s subshell. N value is 4 and S value or L value is 0 for this because it is subshell. So total it becomes 4. Next one, N value is 3 for this subshell 3D, and L value as it is D subshell, L value will be 2. So total it becomes 5. Now for this 4F, N value is 4 and a L value is 3 because it is F subshell. So total it becomes 7. And for this 3s, N value is 3 and S value is L value is 0 as it is S subshell. So total it becomes 3. So which of these is having the same N plus L value as 3p? That is 4s subshell. So here these two orbitals or subshells are having the same N plus L value, 3p and 4s. Now filling of electrons in various subshells present in main shell is governed by. Yes, filling of different subshells present in a main shell is governed by Aufbau principle, because it states that the orbitals the lowest energy will be occupied with electrons first, then only electrons will occupy higher orbits. So this is explained in the Aufbau principle. So the same we see in Euler diagram also. There the subshells with a lower n plus L value will be occupied with electrons first, and then the orbitals or subshells with the greater n plus L values. So this is given in Aufbau's principle. It is explained or governed in Aufbau principle. According to Pauli's principle, an orbital can have only dash electrons. Yes, how many electrons can be accommodated in an orbital according to Pauli's principle? What is actually Pauli's principle? Pauli's principle states that no two electrons in an atom can have same set of quantum numbers. So to have at least one quantum number different, those electrons, an orbital can have maximum of two electrons, one with the clockwise spin, the other with the anti-clockwise spin. So an orbital can accommodate maximum of two electrons only. Then only one will be the clockwise spin, the other will be anti-clockwise spin. Then if you write the quantum numbers for these two electrons, they'll be differed in the spin quantum number. Even though they get three quantum numbers the same, they'll be differed in spin quantum number value. The electronic configuration of phosphorus is, say, we know the atomic number of phosphorus is 15. So if I write electronic configuration for phosphorus with 15 electrons, we get it as 1s2, 2s2, 2p6, 3s2, 3p6. We get 3p6? No. We get it as 1s2, 2s2, 2p6. So this 1s2, 2s2, 2p6 is the electronic configuration of neon. So by using the symbol of neon also, we can write it now. Neon. Till neon, 10 electrons are completed. The remaining 5 electrons will be in the third shell. In S subshell, 2 electrons, and in the P subshell, 3 electrons. And in the P subshell, as we know, there are 3 orbitals, px, py, pz. So according to Hund's rule, each degenerate orbital will be occupied with a single electron first. Now we write it as 3px1, 3py1, 3pz1. Now the electron configuration of phosphorus becomes neon 3s2, 3px1, 3py1, 3pz1. Where it is given, say, yeah, it is. Next, the value of Planck's constant in CGS units is. What is the value of Planck's constant? We know the value of Planck's constant is 6.625 into 10 to the power of minus 27 erg second, or 6.625 into 10 to the power of minus 34 joule second. But here they're asking its value in Celsius units. So erg second or Celsius units for Planck's constant. So in those units its value is 6.625 into 10 to the power of minus 27. Its value. So actually it comes in erg second. They did not ask here units, so we did not write erg second. This value is in joule second or SI units. Now in CGS units they're asking here, so it becomes 6.625 into 10 to the power of minus 27 is a correct answer. Next one. The ratio of the energy of photon of 2000 angstroms wavelength to that of a photon of 4000 angstroms wavelength. See here, they have given two photons with different wavelengths and they're asking the ratio of their energies. Now, let us see solution for this. We know the formula for relation which relates between the energy and wavelength. What is that? Energy is equal to hc by lambda, which we get it from E is equal to h nu, where nu is frequency. So we know nu is equal to c by lambda. If we substitute that, we get it as E is equal to hc by lambda. From this, we can relate energy and wavelength as E is inversely proportional to wavelength. So from this, we can say when you take for two different photons, E1 by E2 is equal to lambda 2 by lambda 1. So here they have given the wavelengths of two different photons. If we substitute those two in this formula, we get the ratio of energies. Let us substitute the wavelengths. So the wavelength of second photon is 4000 and for the first one is 2000. So we get here 2 is to 1. The ratio of energies of these two photons is 2 is to 1. Okay. This we got from the relation E is equal to h nu or E is equal to hc by lambda. Here energy and wavelength are inversely proportional one to another. From this we derived that E1 by E2 is equal to lambda 2 by lambda 1. We got the energy relation here. Next, calculate the energy associated with a photon of light whose frequency is 3 into 10 to the power of 15 Hz. So what they have given here and what they're asking to calculate, if you try to understand those two, we can do easily. Let us see solution. They have given the frequency of that radiation. Frequency of a photon is given as 3 into 10 to the power of 15 seconds. Now they're asking to calculate the energy. What is the relation between the frequency and energy? We have it as E is equal to h nu, and here h represents a constant called Planck's constant, whose value already given here as 6.625 into 10 to the power of minus 34 joule second. Now substitute these values, we get it as 19.878 into 10 to the power of minus 19 joules. Or if you shift the decimals, it becomes 1.9878 into 10 to the power of minus 18 joules. Where is it? In the C. Okay, just we have used the relation between the energy and frequency because they have given frequency and asking to calculate energy. We have a relation between them as E is equal to h nu, where h is a Planck's constant. The wavelength of a radiation is 97540 97,540 centimeters. Calculate its frequency. So they have given here wavelength, asking to calculate frequency. So let us see solution. We have relation between these two as wavelength is given here. The relation between the frequency and wavelength is given by nu is equal to c by lambda. So they have given wavelength and c is the velocity of light, which is a constant. So if you substitute those two values, we get the frequency. See, what did we get here? If you shift the decimals, we get it as 3.07 into 10 to the power of 55 second inverse. Where is it? Yeah, in the first option it is given. Okay, next one. Light of any electromagnetic radiation travels in vacuum or air with a speed of. Yes, all the electromagnetic radiations will travel with the same speed, that is equal to the velocity of light. So these electromagnetic radiations, they travel in the air or in the vacuum also with the same speed, that is equal to the velocity of light. What is the velocity of light? 3 into 10 to the power of 8 meters per second, or 3 into 10 to the power of 10 centimeters per second. Which of these given in terms of meters per second they have given? So it will be equal to 3 into 10 to the power of 8 meters per second. It is correct answer. Next, the equation corresponding to the wave number of spectral line in P-Fund series. So when this P-Fund series is obtained, when it is obtained, when electrons jump from higher orbits to fifth orbit. That means in P-Fund series, N1 will be 5 and N2 will be any higher orbit than 5. That is 6, 7, 8 and so on. Now N1 is 5 and N2 is, it might be any of the number more than 5. That means when electron jumps from higher orbits to fifth orbit, this P-Fund series is obtained. Now the wave number equation is given like this. According to Rydberg equation, wave number nu bar is equal to, we have nu bar is equal to R into 1 by N1 square minus 1 by N2 square. So this is the formula to calculate the wave number according to Rydberg, where R is a Rydberg constant and N1 is the orbit to which electron is jumped, and N2 is the orbit from which electron is jumping. So N1 is the lower orbit, N2 is the higher orbit. Now in the P-Fund series, lower orbit will be always fifth orbit. So N1 is equal to 5 and N2 might be any number which is greater than 5. See in which it is given N1 as 5 in this equation. R into 1 by 5 square minus 1 by 6 square. So in this case, P-Fund series is obtained. This is the equation representing the wave number of P-Fund series line. Okay, next one. Radius of nth orbit in single electron species is given by. So a Bohr has given some equation to calculate radius of the nth orbit for the atom with a single electron as R is equal to 0.529 into n square by z angstroms, where n represents the number of the orbit and z represents the atomic number of that single electron species. So where is it given? Here. R is equal to 0.529 into n square by z angstroms. This is the equation to calculate the radius of the nth orbit of single electron species. Next, the angular momentum of an electron revolving in Bohr's second orbit. So, to calculate the angular momentum according to Bohr, we have formula mvr is equal to nh by 2 pi. Is a formula. mvr is equal to nh by 2 pi. Now they're asking for the angular momentum of the electron in the second orbit. In this mvr is equal to nh by 2 pi, n represents the number of the orbit. So if we substitute n value with 2, we get it as mvr is equal to 2h by 2 pi or mvr is equal to h by pi. So the angular momentum of the electron in the Bohr's second orbit is given as h by pi. Where is it? The second one. So this is actually here p should be replaced with pi in all the options. So h by pi, because the formula to calculate angular momentum is mvr is equal to nh by 2 pi, where n represents the number of the orbit. So as they mentioned in the question as second orbit, we substitute 2 in the place of n, we get angular momentum value totally as h by pi. Next question. Momentum of a photon of wavelength lambda is, so to calculate momentum or to calculate the wavelength of a particle, de Broglie has given an equation, that is lambda is equal to h by pi. So from this which represents here lambda is the wavelength, h is a Planck's constant, and p representing the momentum of the particle or photon. Now they are asking to calculate momentum of a photon with wavelength. Wavelength is given, asking to calculate photon momentum. So keep this as subject, p will come here and lambda will come to denominator. Now it becomes p is equal to h by lambda. Where is it given? The first option. Momentum of a particle according to de Broglie can be given as h by lambda. Next question. Calculate the momentum of a particle which has a de Broglie wavelength of 2.5 into 10 to the power of minus 10 meters. So they have given wavelength and asking to calculate the momentum of the particle by using de Broglie's wavelength equation. Let us see the solution here also. According to de Broglie's equation, lambda is equal to h by p. Just now we have seen lambda is equal to h by p, where p representing the momentum, h is wavelength, lambda is wavelength, h is Planck's constant. Now in this we have to calculate momentum. They have given the wavelength, so keep this momentum as a subject. We get it as momentum is equal to h by lambda. So h value we know as it is constant 6.625 into 10 to the power of minus 34, and lambda value they have given already. Substitute those two values, we get momentum. Where is it given? The second option. So this we get momentum, we get it as 2.65 into 10 to the power of minus 24 kg meter second inverse. Okay, next one. Calculate the uncertainty in velocity of a cricket ball of mass 150 grams if the uncertainty in its position is of the order of 1 angstroms. So they have given the uncertainty in position of a cricket ball, and they ask to calculate uncertainty in its velocity. According to Heisenberg's uncertainty principle, we have a formula which is relating these uncertainties. That is delta x is equal delta x into delta p is equal to h by 4 pi. This is a uncertainty principle equation according to Heisenberg. The product of the uncertainties in the position and momentum is equal to h by 4 pi. Now, here they're asking to calculate the uncertainty in the velocity. So this position can be written as, we know momentum is equal to product of the mass and velocity. So momentum can be written as mass into velocity. Mass is being constant and there will be uncertainty in the only velocity. This can be written as delta x into mass into uncertainty in the velocity delta v. So this can be replaced with this. Now we can calculate delta v. Let us see solution. So given mass as 150 grams, let us convert this into SI units, 0.15 kgs, and the uncertainty in the position delta x is given 1 angstrom. Let us convert that also into SI units, 10 to the power of minus 10 meters, because we know 1 angstrom is equal to 10 to the power of minus 10 meters or 10 to the power of minus 8 centimeters. Next, Planck's constant also let us take in the SI units, 6.625 into 10 to the power of minus 34 kg meter square per second. It is already given in the problem, so let us take as it is. Now we have the formula delta x into m into delta v is equal to h by 4 pi. In this we have to calculate delta v. Remaining all values are given. So substitute those all. We get as delta v is equal to h by 4 pi into delta x into m. We get finally 3.5 into 10 to the power of minus 24 meters per second. That is uncertainty in the velocity. Where is it given? Here. Okay, next. The size of the orbit is given by the quantum number. Yes, each and every quantum number represents one particular property of the electrons. So here, out of those four quantum numbers, the first quantum number, principal quantum number, indicates the size and energy concerned to the particular orbit. So size and energy are given by principal quantum number n. Azimuthal quantum number gives the shape of the subshell in which electron is located, and magnetic quantum number represents the orientation of the electron. That means according to which axis that electron is revolving is given by magnetic quantum number. And the spin quantum number gives the self rotation of the electron, either clockwise or anti-clockwise. So here size is given by n. Next, if the electron is spinning in clockwise direction, its spin value will be plus half. If electron in the clockwise spin value will be plus half. It is in the anti-clockwise spin value will be minus half. Which of the following options does not represent ground state electronic configuration of an atom? So, in the ground state or general configuration, atoms will be, the electronic configurations will be governed by those principles. One of them is Abbo principle. First, all the lower energy levels will be filled with electrons, then only higher energy levels will be occupied. Now, if you observe the first one, here at the ending, instead of completely filling this 3D subshell, electrons entered into 4s. This is incorrect according to Abbo principle. What does it states here? Above principle states that first lower energy levels should be completely filled with electrons. So after filling this 3D subshell with completely with 10 electrons, then only electrons should enter into this. But it is given wrong. So this is a incorrect electron configuration. So this represents a excited state. Instead of being the electrons in the lower energy levels, if they jump to the higher energy levels, then that's said to be excited state. It is not ground state electron configuration. Okay, this is incorrect. Of course, you may get out here also. Here, instead of completely filling this 3D, electrons entered into 4s. So this is correct only, but according to Hund's rule of maximum multiplicity, atoms with completely filled or half filled electron configuration, their valence shell will get some extra stability. For that, one electron jumped from 3D subshell to 4s here. So it is a ground state configuration only, as only this is a excited configuration. Okay, last one. The pair of ions having same electronic configuration. See here, they have mentioned some metallic ions here. Asking to calculate which are having same electronic configuration. Here if you observe, iron plus 3 and Mn plus 2 will be having same electronic configuration. That is represented as 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d5. So for metallic ions, to avoid the confusion, first write the electronic configuration of the complete metal atom in the ground state. Then, as per the charge mentioned in those ions, remove those many electrons from their outermost energy levels. For example, if you see iron, this completely can be written as argon. So we can write for iron as, what we can iron electron configuration as it is 26 argon 4s2 3d6. This is the electronic configuration of iron. Now here it is mentioned Fe plus 3. That means 3 electrons are removed. Now let us write the electronic configuration of iron plus 3 ion with 23 electrons, because in iron there are 26 electrons. In Fe3 plus means 3 electrons lost. So argon we write as this for the 18 electrons. But here, instead of removing electrons from here, first electrons will be removed from the outermost orbital. Out of this, the outermost orbital is 4s. So from this, 2 electrons are there in that. Totally 2 electrons will be omitted or removed. And totally 3 electrons to be removed. So after removing 2 electrons here, one more electron is removed from 3d5, 3d6. So it becomes now 3d5. So this is the electron configuration of Fe plus 3. So in this way, to avoid the confusion in writing the electronic configuration of different ions, we can follow this. First we can write the configuration of complete neutral metal atom in the ground state. Then we can remove the number of electrons as its charge mentioned from the outermost orbitals. Now Fe plus 3 ion and Mn plus 2 ion are having the same electron configuration according to this. Okay, this is the correct answer. Thank you for watching our video. Please subscribe our YouTube channel Aims Today for latest updates and recorded videos. Thank you.